When thinking about acid-base titrations, we could measure the pH, but we also often use indicators to let us know when our um, solution is more acidic or more basic. When we looked at indicators before, I mentioned that acid-base indicators are normally either weak acids or weak bases, depending on your perspective themselves. That means that they can accept or donate some protons, and what we see here is that they change color as a result. The extra hydrogen ion changes the shape, it changes the way it absorbs, reflects, refracts, transmits light in terms of all of those things. So in one side or in one of the solutions, in one case, it has the hydrogen ion and has a certain color. And once it's lost that hydrogen ion, it has a different color. This is often represented by kind of a generic equation because we'll see these indicators are often very complex molecules that we have the protonated version of my indicator that has one color and the deprotonator equation or version that has the other. The charge can vary where this could have a positive charge and that could be neutral. But the idea in this is when I add more hydrogen ion with Le Chatelier's principle, that causes it to shift this way. So when I'm in a solution with a very low pH, we shift to the left and get more of this. When the pH rises and I either have less hydrogen ion or we think about maybe more hydroxide ion, we're removing this. So it's shifting to the right, producing more of the In minus form, the conjugate base or deprotonated form. For that, we have to think about this and this, just like in the last video, the HIN and the IN would be equal when the pH equals the pKa for that acid itself. Now we think about, well, if the pH is below that, that means that we have more of that acidic version, just like previously, but now we're applying it to the indicator itself. That would be the acidic color. That would be phenolphthalene's colorless version. Once the pH goes higher, once we are taking the hydrogen ion from that, once we put more hydroxide in, all different ways of saying the same thing, it becomes more basic. The equilibrium shifts to the right, giving us more of the deprotonated version, the anion or conjugate base version, and then it turns to the other color. In this case, it's the pinkish color for phenolphthalein. So with an indicator, if you are asked to choose, you want to match up the pKa of the indicator to the pH change that you can expect for your solution. So I'm going to scroll back through some important highlights that will help us with that. So once again, we would need to think about, well, am I titrating strong with weak, weak with weak, weak with strong, to recognize will the pH be above 7, below 7, or equal to 7? And then right here, we would maybe be given some color changes, but we're really looking for the pKa, or here they label it as the pKin for the indicator itself.